All right, so let's continue our afternoon session. So we continue with the actually Marx's laws. We lost Marx. Let's wait a little bit. Done. I think we got that. Let's wait. All right, so we continue with the presents from Stony Brook for Marx's birthday. So it's a great pleasure to introduce John Parker, who is going to tell us about generic transversality in complex geometry. John?
Thank you very much. I'm very happy to be here and to be able to be part of celebrating vaccine and have all the beautiful mathematics given to us. So my talk will be about generic transversality in complex geometry. This is talk I've given a number of times, but it's disguised. I've given this a new title, a new abstract, and rearranged things. So if you've heard me give it before, the exercise is trying to compare the two, trying to see what I can promote. Okay, so I'll begin by stating, well-known result, just elementary, from almost complex geometry. So, for generic, almost complex structure J on manifold X, all simple, and that means not multiply covered maps. Let's see, which will be a smooth connected Riemann surface. X, specifically pseudo-holomorphic maps, J-holomorphic maps. All simple J-holomorphic maps are unobstructed. Now, this is usually taken as sort of a foundational fact for, say, defining invariants, enumerative invariants for symplectic manifolds. So that's usually why the generic transversality results are interesting. Means we don't have to work too hard to define original fundamentals. Now, there was this recent, not so recent work of Ionel Parker proving the Gopakumar Vafa integrality conjecture, and the core of their argument is actually use of generic transversality. So, Gopakumar Vafa integrality conjecture, some conjecture about Gromov invariants of certain linear combinations are integers, and they use this elementary fact to reduce that fact, to reduce that statement to a statement about isolated curves, the local case, isolated transfer. and which was essentially, well, and then they proved that case by reusing it in the calculation. So this is more than a result, which is sort of useful for technical convenience. So let's just recall one line of the proof. So it's equivalent to show that equivalently the total space, total universal multiplied space consisting of pairs J, U, with U being J homomorphic, is unobstructed. This result says that something holds generically. We're going to prove this result says something holds everywhere. And then SAR's theorem will tell us that this generates system. So really we have to prove this. And this is just something being surjective. So this amounts to showing that tangent space, another space of almost complex structures you want to consider, plus this deformation operator associated to C. This is surjective. That's what we want. And the second component here for C infinity, this is an elliptic operator. It's covariant, it's bidimensional, and how to say, you can detect elements of the covariant by pairing with any Bump function locally anywhere. So if you have any reasonably non-trivial family of J at all, whatever you like, smooth, almost complex structure, real analytic ones, you will be able to surject on the covariant. There are only finitely many dimensions you have to surject onto, and you have infinitely many ways to be one. That's very easy. Using basically any reasonable class of almost complex structure. Okay, so I want to state that the analog of this in complex geometry, and it's sort of a trivial level, but I haven't really seen it used for anything other than this one I talked about. So the X, E, A. And just right off the bat, I want to remark that if you have a complex manifold, you know, they're almost, it's very often the case that there are zero definitions, but the definition space is always like prime. So we really require to go a large collection of J's to be able to do. There's no hope of anything like this on a complex now. So if we just start with something arbitrary, we're going to have to change X a little bit to have any sort of thing like this true. So that's a D. An X that is n dimensional, and D would be n minus 1 dimensional. Would be a divisor with boundaries. So really, that just means this is isomorphic to the unit disk in C to the power. And I'm going to assume this. divisor isomorphic. You could make this more general. It just needs to be like something affine or something. Let's just leave it with purposes. Then generic regluings of x minus boundary divisor. What's here will be x, and the divisor is just sitting inside somewhere like this. And I'm going to remove the boundary. That's removed. That's the non-compactness we need to make things transverse. So now, after having removed this, you can write this x minus boundary as a gluing of two pieces. So roughly the two pieces are the neighborhood of D and the complement of D. So this is, I guess, x minus D union the neighborhood of D. The union is over neighborhood D minus D function. So for generic regluings, all simple J-holomorphic. Well, there's no J now, there's just complex manifolds, so all simple holomorphic maps which intersect D. Intersect D are obstructed. So a map like that is going to look something like this. So it intersects D. If you have some C prime over there, well, we haven't changed it. You can't expect this one unobstructed. We haven't done it. But as long as C intersects this region where you're doing the regluing, then you can make it unobstructed. Now, is again more or less trivial. Before getting it, maybe I should say a little bit more about what I mean by regluing. So these are two pieces, the complement of D and neighborhood of D. They intersect over the function neighborhood, and you can reglue by any D in, I shouldn't say D. I'll write. It's not the few ones. The complex manifold automorphisms of neighborhood D minus D gets you an XD, which is, I would say, X minus D union over this regluing. You will glue these together by the transition of D. Now, it's a little bit hard to make this precise because these are non-compacted to say where exactly you're doing the gluing. This probably doesn't have any automorphisms, so really you're cutting away some neighborhood and infinity, doing something over a compact set and gluing it. But that's the technicality.
Is looking there along some common boundary?
Sorry?
Is looking there along some common boundary?
Yeah, well, yeah, so it's not really a boundary because it's code dimension 0, it's full intersection that we're gluing along. Yeah, so I think a good analogy to have is that considers a Riemann surface sigma, I'll call it sigma, so we don't get confused with C. And you pick a point, then you can write sigma as the union of sigma minus P. And disk around P over the puncture disk at P. From that scene a long time ago, you can explore the entire local moduli of Riemann surfaces near sigma by changing kind. Great. So let's think about proof. Again, it's going to be some simple calculation. So what we want. So the result about subjectivity of some map. And what's the map? It's the map from the tangent space to the holomorphism, such as vector fields. Vector field is a first order way of changing the way we move. That's H naught of, I guess, neighborhood of D. The coefficients in tangent X listed by D. So that's when you have a lot of holes on B. And this should go to the obstruction space of the curve. Obstruction space of the curve. Mapping in, that's H1, C, U upper star, Tx. And so we want this to be surjective, but this is this map. You can factor it through. First, you take sections of C. This is Tx within the modulo Tx. That's the quotient of coherent sheaves, and this is the connecting homomorphism homological exact sequence associated with that short exact sequence from Tx to Tx infinity D quotient. And so that exact sequence continues H1 C U over star Tx of infinity D, and this is 0, right? Because it's 0 if D intersects C, because that is a very powerful line. So that means by exactness this is surjective. So that right, and then you want to also show that this is surjective. But after, yeah, right, affine-ness of D, the fact that D is a very simple thing, means this is surjective. That's an explicit section. Surjective. Okay, so now let's try to see why this result is actually useful for anything. So it's deficient in the fact that it requires you to make your manifold smaller. It has to remove the boundary of D. And so if you want to study the moduli space of any moduli space of holomorphic curves, you make it transverse, like you can in Ionel Parker's proof of the Gopakumar Vafa conjecture. You're sort of out of luck because you can only make it transverse over neighborhood. Well, maybe transverse over unobstructed over neighborhood of one particular curve. Maybe some others if they are, you're lucky. But generically, the moduli space of the curve you care about to cover all that, so there's no room to do this perturbation. So to get around that, there's this So I'm going to try to explain what this is. So suppose we associate to any complex manifold any moduli space of configurations. It could be holomorphic curves, it could be holomorphic cycles, it could be stable pairs, a sense of under the comments, it could be instantons, and anything you like. Moduli space of objects. With the virtual fundamentals. So then, given any homology class, which we usually call insertion, we get this number, this graph. Graph trick seems pretty trivial, but let me explain what it is. Right, first of all, I need a generalization of this out of the families. So now, if I have a family, X over B, family of things which used to be called X. Now, I get E of X over B over B. So that's just as a set, it's moduli space associated to all fibers, but of course the apologize appropriate. So more generally, right now you can consider family invariants. If you have homology class of E of X over B, you can integrate. So what the graph trick will do is it will reduce one of these invariants to another invariant in which the cohomology class gamma is supported over a subset which maps injectively to the base. Or in other words, the configurations you're counting with this invariant, well, there's only one of them that you actually care about in for every manifold in your family, and most of them. Okay, so it's sort of trivial, but it's the key step to making generic transversality for complex manifolds useful for anything. So graph trick. So we have this integral over xp. Virtual, then I can do something very silly, which is I can consider this new family, which is x times Rn over b times Rn, just multiply the base by the space. And of course now so what's this new multiply space that is same multiply space as before times R. variant of this new family. And I can't just take gamma because that's the wrong dimension. The original dimension of this is now n larger, so I need to cut this class to something dimension n to make it 0 for 0 for point radials. The origin regenerated. So this says nothing at all. It just says consider this large family and then add a constraint that I have to meet 0. But now, what we observe is that we can write this a little bit different. We write this as integral same space. And minus I. That projection to Rn and projection to Rn minus I are homotopy. The logical class should go back to the same. Relaying to be properly homotopy, so maybe we should be assuming this is compact. And we're done. That's it. So now the key is that this cohomology class, this new cohomology class, is now this supported inside we need to take gamma into account. So just this the smaller piece, this thing. This is supported inside the graph of I inside inside the space X over B. So B I to R, that's the method. So the map to this base is certainly also an method. So the takeaway is every family to variant or E is equivalent, basically canonically, to one whose insertion gamma in this cohomology EX over B is supported over some compact K. Now the B is injected. So that's precisely what I said at the very beginning of this graph trick would do. It takes the arbitrary enumerative invariant. Some insertion. As you write says one for a different family, but with the proper appropriate that it only cares about one configuration for each of the manifolds in the family. So this is the first thing you need to do to make generic transversality for complex manifolds. You can get any mileage on it. There's a second thing you need to do. That you need to pick the divisors you use. So it's possible that you could define ways of perturbing complex structures in other ways which don't use divisors or which are a little bit more flexible. But hey, the divisor method is what we're only one I know at the moment. So second, yeah. Using generic transversality is enough divisors. Well, that's, so the X B down complex. And K side Z X over B be compact. And the map to B should be injected. So I should explain what Z is. Z is the space of cycles, holomorphic cycles, one-dimensional holomorphic cycles. I have X, then a holomorphic cycle would look like this. Has a bunch of singularities, each irreducible component comes with a multiplicity. That's holomorphic. Z of X is given by a formal sum. Ionel. Topology of the space is such that the cycle nearby to this, this cycle nearby is supported in the neighborhood. And if you look at the neighborhood of this multiplicity 7, it might split into a bunch of things locally, but there's 7 of them. Count multiples. Singularities can resolve. So that's the space we want to consider. That's the large space of configurations. So after by that I mean you're allowed to throw away any part of any closed subset X disjunctive. Throw away closed subset X disjunctive. subset. Okay. And there exists now disjoint relative divisors di is inside x times b ui open. So which are disjoint. Oh, everything in K. Oh, everything in K. I just mean that for every cycle in K, all of its irreducible components intersect some di. So let me explain why do we need this. Well, if we want to make everything in K to be transverse, then we should have a divisor intersecting all the irreducible components of everything. Because then it's the Laplace lambda form using that divisor, since it intersects all the irreducible components, we can make it transverse. And they have to be disjoint because this regluing doesn't make if I two divisors intersect, I can't reglue on both at the same. At least I don't know. Great. So it's trivial local. So that is to say, if I have K as a single point, single curve, single cycle, then I can certainly make a divisor which intersects it. That's local construction, making divisors like that, just a local. And I'm allowed to remove the boundary from X. And then I can do. So the whole point is how to make this trivial construction work in a family. So if we try to work in a family, the chosen divisors may intersect, but we choose them generically. The only bad locus is codimension 2 subset. Okay. So I have a bunch of divisors, and they're moving around. That's what's the codimension of a condition that they intersect. Well, we're in a general complex manifold. Divisors generically intersect. It's definitely not codimension 2. But remember, we're allowed to throw away anything far away from cycles. So really, we're asking for two divisors and a curve to intersect. That intersects that. If the two divisors intersect off the curve, I don't really care, just make them smaller. So it's really about down points on the curve. And when do they intersect? Well, the points on the curve intersecting is codimension 2 condition. If we just choose a divisor generically, the codimension 2 subset of that, okay, we should that for calculus our goal. But we've at least improved the situation in the sense that we've reduced to a smaller K. And now if we solve the problem over this codimension 2 subset of K, then we just add these divisors with the way of the subset. So, now use reduction on mentioned. Okay. Now, there's a subtlety in the induction hypothesis needs to be a little bit stronger. The induction hypothesis needs to be that you already have some chosen divisors, and you need to avoid that with the new ones. But again, that's going to be co-dimension to locus where accomplished problems. So that works. Okay, so that's right. There's an additional let's recap. So we have I stated generic transversality for complex manifolds, and a priori this isn't something which can be applied to moduli spaces because they're too local. But I give you two ingredients whereby I can change a moduli problem to one, change the enumerative problem to one, which only cares about one cycle in one particular cycle in your family. And we should have hook up the divisors so that we can make the cycle space transverse, the space math transverse in a neighborhood of such a configurations. So now all that's needed is to write down perturbations. So given divisors, and then reglue our family by any collection maps bi from ui to h naught x coefficients in t x over b within di. Yeah, I guess this should be ui. Let me rest right there. Y t x over b divided by d. Where bi is some compact support. So here's our base. There's some open subsets U, and the divisor only exists over U. So if I want to reglue my family using that divisor, the parameter of that regluing has to be some supported inside UI. It can't be supported anywhere else. The gluing doesn't make sense. So this means we need to expand the class of families we want. There are a few options. One option would be to allow the base B to be a smooth manifold, sort of have what you might call a smoothly family of complex analytic manifolds parameterized by a smooth base. So the transition function should be majorly smooth and fiberized forward. Right, because you're never going to find a PI which is relevant. And then for example. So this you need to either PI smooth or BI piecewise real. So anyway, I chose to take DDBs. You could probably take it to be sequence. That's not a big issue. Either way, you have to enlarge the collection of bases you consider. So far, the base could always be in the same category. It should be complex stuff. But we need to enlarge the category to have enough variation. So that's find the third ingredient. Third ingredient to apply this generic transversality in complex geometry lemma and get anything else. We have to enlarge the category from the category. It doesn't work with the base complex analytic. We have to allow the base either to be smooth or yeah, so this entails making B smooth. So IEB is there's C infinity manifold. And here the B is, well, piecewise real analytic, or maybe a simple shell. So the simple shell complex is the one that decided to use technically implemented. Maybe we can try to take a look at the applications of this discussion. So, beginning of the talk. So there are lots of ways of enumerating curves in complex threefolds. There's this great paper by Pandharipande Thomas called 13 ways of counting curves. And they don't work for all of those. But there are two which are the most common, probably the one with invariants and Donaldson, Pandharipande Thomas invariants. Roughly speaking, they correspond to counting curves using maps. That's in map from C to X. Yeah. The same as well as space of stable maps. They do it for a long lieutenant. Variants. Other invariants, all definitions a little bit complicated. It's called stable characters. Definition is due to Pandharipande and Thomas. And basically, the idea is now counting curves. Now we're counting curves by cutting them out using equations. So coherent sheaves or ideal sheaves correspond to now PT of X equal X Q to the there's a minus somewhere. This is conjecture. I'd like to say something general to start off with. There are lots of calculations of enumerative invariants of complex threefolds, and they all suggest that there's basically only one way of counting, despite the existence of so many different ways of defining curve counts. Aren't related in any obvious way in their definitions. There's no way of producing genuinely different ways of counting curve. They're all always given answers which are related by change in variables. And one particular interesting one, due to modeling, for example, Gopakumar Vafa in this very special case that conjectures that were threefold of these variants are related by this change of variables. U equals minus into that, right? Which is a very interesting change of variables because this is formal expansion around U equals 0, which is set on this transformation U equals 1. Well, this is a formal expansion of U equals 0. So it's not something you can check by just comparing any of these coefficients. Okay. So the main result of the talk, which I gave you all the ingredients for, is following. So this group this is what you might call the universal insertion space. So it's just the co-limit over all families of threefolds of this relative space of contact supported cohomology. This space is where insertions live. Space of cohomologic classes which you compare with virtual fundamental cycle to get an enumerative invariant. So this is sort of one strong way of saying that enumerative invariants of at least Calabi-Yau threefolds are determined uniquely by what they do on local curves. So local curve element roughly corresponds to count curves in degree m on a vector bundle of rank 2 for curve G is G. Okay. Semi-Fano plots. The semi-Fano cycles. This is the locus. Cycles. Comments. No. Class. So it's long-standing problem with symplectic geometry, specifically enumerating pseudo-holomorphic curves. What to do And that in order to apply generic transversality, well, you have trouble with multiple covers. And the trouble you have is that if you have a curve and you look at its multiple covers, they might have smaller expected dimension than the curve you start. And then this is precisely the inequality which prevents that from happening. So generic transversality is something about symbol maps. To use that to control multiply covered maps, you need this inequality. Okay, so the corollary is that this conjecture holds only if it holds for local curves. And this case of local curves has in fact been noted in many cases for a long time. Local curves was sort of the first case where it was computed. Bryan, Pandharipande. Grow up with them inside. Pandharipande did that. In the stable pairs. So, yeah, it'd be interesting to see other other applications of idea generic transversality complex geometry. I guess any place where it's used in symplectic geometry, you could ask whether you can do a similar result in complex geometry using it. There are no Pandharipande Thomas or Donaldson Thomas invariants in symplectic geometry as far as we know. I mean, there's some proposals in some simple cases for what to do, but almost complex six-dimensional manifolds don't have any dimension of coherent sheet we're aware of. So this result, or basically something equivalent to this result, is contained in Ionel Parker's paper for almost complex geometry. They proved, they didn't state it, but they proved basically this result. The analog of this result for almost complex manifolds. But for almost complex manifolds, basically you just have remote invariants. There's not so much application. This corresponds to freely generated property. But for complex geometry, we have all these invariants. So you can get a little bit more mileage on it. Yeah, so I mean, there are many generalizations of this conjecture. This result here only tells you about primary insertions. Insertions coming from cohomology of its cycle space. There are also descendant insertions which are more complicated to understand. And I don't understand them really well. Say whether or not this could be used to say anything about them. I'm cautiously optimistic that so I've been talking with Rahul Pandharipande, and we talked about trying to generalize this to the relative set. Relative stable pair invariants for actual smooth divisor, and now you have this stronger this is a positive condition. So really, I think that the most interesting question is how to remove this positivity condition. I really have no idea how to say anything about structures group, or if it is conjecture for, if you remove this assumption on the first trip possibility of the manifold in question. So maybe I'll answer. Happy birthday to you.